Hello and welcome back. Today again we're going to talk about group homomorphism, but today we're going to talk about the image of an homomorphism. So what is the meaning of the word image of an homomorphism? So first of all, let me talk about that. We have two groups. So let Z with the composition and G dash with another composition are two groups, or be two groups. So now suppose we have an homomorphism, so let phi from the group G to G dash be a homomorphism, homomorphism, which means, so let me again recall that what is homomorphism. Homomorphism means, so phi is a mapping from the group G to the group G dash satisfy the property that phi of A plus B is same with phi of A plus phi of B. Now because phi is a mapping, so we can talk about the image of that mapping. So what is the image of a mapping? So image of phi is basically the collection of all the values phi of x such that x belongs to the set G. So let me recall that what is the image of a function. Suppose we have a function from a set A to the set B. So where A is, suppose A is 1, 2, 3 and B is our set which is A, B, C, D. So this is a function. So let me define how the function is defined. Let me define the function. So here A is a set, non-empty set, B is another non-empty set. Let me define the function f from the set A to B. So sorry, which means if assign the elements of the set A to the set B, then for example if assign 1 to the element A, if f of 2 to the element B, f of 3 to the element C. So in this case the image of f, the image of f is the collection of all points of B, is the collection of all points of B where some point of A are mapped. Image of f is a collection of all points of B where the points of A are mapped. So here you can see that in the point A the 1 is mapped, in the point B 2 is mapped, in the point C 3 is mapped. So image of f is collection A, B, C. Why here is no D? Because there is no other point in the set A which is mapped to the point D. So in this way image of f is defined. So let me define another function which is G from the same set A to the set B. Now G is defined in this way that G of A1 is D, G of 2 is C, G of 3 is again C. So in that case image of G is, again you can see that only at the point C and D of the set B the points of the set A are mapped. You can see only the points C and D are the points of the set B where the points of A are mapped. So here the image of G is the collection C and D. You can see that for this mapping there is no point of the set A which is mapped to the point A. Also there is no point of the set A which is mapped to the point B. So image of G collection of only the collection of the points C and D. Similarly, so here is the definition. So similarly if we have two sets G and G dash and phi is an homomorphism, then image of phi is a collection of all points of G dash. So image of phi, you can see that this is the subset of G dash where the points of x, point of the set G, where the points x of the set G mapped. So x is mapped to the point phi x by this mapping phi, and we are taking collection of all such values, all such image of the point x. So that's why this is called the image of the function or the homomorphism phi. So what we're going to do, we denote by the notation. So instead of image of phi, in some books you also can see that this type of notation. So these sets also denoted by. So let me first erase this part, then let me talk about that. So here we go. The image of this set is a subset of G dash, and also in some books we can see that the notation is that image of phi also denote by this sign, that phi of G, which is same, again the same. Phi of G means, which means image of phi, that means phi of G is a collection of all phi of X such that X belongs to the set G. So it is the collection of all the images of the elements of G. Now here is a beautiful results over here. So it says that let me write down the result. It's a very beautiful result. So results is, so it says that let Z and G dash be two groups, and phi from G to G dash be a homomorphism, then what we have, then we already seen over here the image of phi is a subset of the group G dash. So result says that this is not only a subset but is a subgroup. Then the image of G, which is phi of G, is a subgroup of the group G dash. Okay, so image of G, which is phi of G, is not only a subset of G dash but it is a subgroup. So that's the very important thing. The phi of G has some structures, some algebraic structures is there on the set phi of G, so that it's become a subgroup of the group G dash. This is a very, very important results over here. So before that, let me inform you that the image, the phi of G, because phi is an homomorphism, this is also called the homomorphic image. So this is also called the homomorphic. So we will going to use this word homomorphic image because phi is an homomorphism, and this is the image of the set or the group G. So phi of G is a homomorphic image of the group G. So this is also the word we're going to use. So this is phi of G is called the homomorphic image of the group G. So here let me, the proof is not for you, the results, the proof of the results you don't have to memorize for your exam, but let me give you the proof. It's for completeness I am giving you the proof of these results, that how to prove that phi of G is a subgroup of G dash, because I want to complete the course over here, and also I give you one more test to check how to check one more test to check a subset is a subgroup or not. So that's why I will prove that phi of G is a subgroup of G dash. So first of all, let me erase the all portion. So here we have the proof of the results. Proof. What we're going to do, we have a mapping phi from G to G dash. We show that phi of G is a subgroup of G dash. So you can see that. So what it means, suppose we have the set G over here, and here we have the group G dash over here, and somehow we have this, that the image of this whole group is over here, some subset of G dash. So suppose this is phi of G, so this is a subset of G dash, so phi of G is a subset of G dash. Now this subset with the same induce operation from the group G dash become a subgroup. So first of all, what we know that, so before that let me write down that let EG and EG dash are the identity elements of the group G and G dash respectively. So EG is a identity element of the group G and EG dash is the identity of the group G dash. Now what we know from our previous results, that we know that the image of the identity elements of the group G is the identity elements of the group G dash. So we know that this is from a previous result. So this is our results 1 of group homomorphism. So this is a result 1 of the homomorphism, the topic homomorphism. So we know that EG is equals to EG dash, because EG is an element, EG belongs to Z, so phi of EG belongs to phi of G. That's the very simple, which means EG dash, phi of EG is EG dash, so EG dash belongs to phi of G. So you can see that the condition 1 is satisfied. So condition 1, which is the condition 1, if the subset must contain the identity elements of the group. So first condition is satisfied, so condition 1 holds. Let's talk about the condition 2. For that, what we have to take? We have to take two elements. So let A dash, B dash are two elements belongs to the set phi of G. What we have to show? We have to show that A dash star is a composition on the group G dash. So A dash star B dash belongs to phi of G. Now what we know? So let me write that down. Now A dash belongs to phi of G, which means, let me again write, what is phi of G? Is a collection of all x, phi of x. X is an element of G, which means A dash must be, which means therefore A dash equals to some phi of A for some element, some A belongs to Z, because all elements of phi of G is of the form phi of x for some x of the group G. So A dash must be equals to some phi of A for some elements A belongs to the group G. Similarly B dash, so let me erase this part and write over there. So here we go. So condition, we have already seen that condition 1 holds for the subset phi of G. Now we are checking about, we are trying to verify that condition 2 is hold on or not. So B dash will be same with some phi of B for some element B of the group G. So what about now? What we know? Now we know that A dash star B dash is equals to phi of A star phi of B. Now since phi is an homomorphism, so we can write this is as A compose B. Since, let me write over, since phi is a homomorphism, so we can write in this form. So now you can see that because G is a group, since A, B belongs to the group G, because here we choose A belongs to G and here B belongs to G, so A, B belongs to G means since G is a group, so A compose B also belongs to G. So because A compose B belongs to G, so phi of A compose B obviously belongs to phi of G. So that means A dash comma B dash, which is phi of A compose B. So this implies A dash star B dash belongs to phi of G. So condition 2 holds. So 2 holds. So these are the conditions. So first condition and second condition to verify the subgroup subset is subgroup or not, it holds. Now check for the condition 3. So let me write down the condition 3. So condition 3 is almost same with the condition 2. So but let me write it down over here. So first of all, let me erase this part. So here we go. Yeah, we have to go through this process over and over again. Okay, so now we are talking about the condition 3 is hold or not. So let A dash belongs to phi of G. What we have to show? We have to show that A dash inverse, the inverse of these elements, also belongs to phi of G. Now what we know? Now A dash belongs to phi of G, and phi of G is a collection of all phi of X, and X is an element of G, which means A dash must be equals to some phi of A for some A belongs to the group G. Now let me write, now A belongs to G imply A inverse belongs to G. Then what we know from our previous result, that phi of A inverse is same with phi of A whole inverse. So now phi of A is equals to A dash whole inverse. So A dash inverse is phi of A inverse, and A dash belongs to G means, so let me write over here, A dash inverse is basically phi of A inverse, and A inverse, since A inverse belongs to G, so phi of A inverse belongs to phi of G, which means A dash inverse belongs to phi of G. So third condition is also hold over here. So thus phi of G is a subgroup. Thus phi of G is a subgroup. If you forget about the methods, so I will recommend you to go through my previous video, or also you can look over you can look into the our notes, lecture note 3. So here we go, but let me over here, let me tell you what to do, how to check quickly. Let me quickly say, so a subset H of group G is a subgroup if and only if you have to check that identity element of the group belongs to the set H. Second condition, you have to check that if two elements belongs to H, and this will imply that A compose B belongs to H, and this is true for all AB. And third condition is for all A belongs to the set A H, the A inverse have to be in the set H. If three condition hold, then H is a subgroup of G, and if H is a subgroup of G, these three condition also hold. So this is the if and only if conditions. So to check a subset is a subgroup or not, you have to check these three conditions. So here we have seen that phi of G is a subset of G dash and satisfy all of these three conditions. So phi of G is a subgroup of the group G dash. So in some book also you will find this word results. This is the same results. So it says that the homomorphic image image of a group is a subgroup. You also can find statement like this. They are the same statement. The homomorphic image, which means if we have a phi which is a mapping from G to the group G dash, then the homomorphic image of the group G is phi of G, and we already seen that phi of G is a subgroup of the group G dash. So they are the same results. Okay, so in this way you have to learn. So let me quickly give you a few more statements over here, so that you do not have proof of all these results, today's results, and also I will going to state two results. You do not have to memorize the proof, just you only have to understand the proof. So next two results you can also learn about these results. So remember these results. So if G is a commutative group, G is a commutative group, remember that this will imply then phi of G is a commutative group. So this is one of the results. So if G is a commutative, then homomorphic image, which is phi of G, is a commutative. And second result says that if G is a cyclic group, so these results may become as an MCQ type questions. So if G is a cyclic group, then remember that the homomorphic image, which is phi of G, is a cyclic group. So homomorphic image of a commutative group. So please listen very carefully. The homomorphic image of a commutative group is commutative. The homomorphic image of a cyclic group is cyclic. Okay, remember that part. So homomorphic image of a cyclic group is cyclic, homomorphic image of a commutative group is commutative. So they are two results. You have to may come as in some MCQ type questions, and maybe you have to use these tools to prove our some future results. So before that, let me quickly give an example, give an quick application of these results too. So let me give an application of these results too. So here we have application of this previous result. So application of the results too. So it says that so this is one of the problem. You can show that there is no onto homomorphism, which is also called the epimorphism. I think it's called the epimorphism. There is no onto homomorphism from the group. So from the group Z4, onto homomorphism from the group Z4 to the Kalian 4 group. So let me write down the group Kalian. So KLY, I think. So what is that? So let me Kalian, KLEYIN. I forgot the spelling though. So let me write down the group actually. So Kalian 4 group, I think you remember the group V, which is contain the 4 elements E, A, B, C, and so there is no onto. It says that there is no onto homomorphism from the group Z4 to the group V. V is the Kalian 4 group, which contain the 4 elements E, A, B, C. So how to prove these results? So let me write that down. So first of all, what is the onto homomorphism means? So which means if we have an homomorphism from Z4 to the group V, if it is an onto means the image, onto means each element of V has an pre-image. Each element of V has an pre-image. So since phi is onto, so since phi of is onto, so phi of Z of 4 is whole set V actually. So this is the form, the definition of the mapping onto. Mapping F from, let me remind you, a mapping F from A to B is called onto mapping or surjective mapping if the range set or the image F of A, which is also called the image of F, is the whole set B. So here the B set B is B, so image of Z4 is equals to V over here. So what we have to show that there is no onto homomorphism. Now let me remind you that Z4 is a cyclic group. So it's a cyclic group generated by 1 bar. So Z4 is a cyclic group. So Z4, I am talking about Z4 plus, this is a cyclic group generated by 1. So let me quickly remind you. So 0 bar is 0 into 1 bar, 1 bar is 1 into 1 bar. What is 2 bar? 2 bar is 1 bar plus 1 bar. What is 3 bar? 1 bar plus 1 bar plus 1 bar. So 2 bar means 2 into 1 bar, and here we have 1 into 3 bar. You can see that each elements of the group Z4 can be written as an linear, as an expression or some integral multiple of the element 1 bar. So Z4 is generated by the elements 1 bar. So Z4 is a cyclic group generated by 1 bar. So when I was talking about cyclic group, on that case I had seen you that B, the group Killian 4 group, is not a cyclic group, So quickly, let me quickly remind you the composition table for the set V or the group V, which is A, B, C, E, A, B, C. If you forget about the results, I will recommend you just go to my previous video. Some previous video you will find about the video about the cyclic group. You will find that we have shown that V is not a cyclic group. So it's E, A, B, C, A, B, C, A is E, A, B is C, C, A is B, B, A is C, B, B is E, B, C is A, C, A is B, C, B is A, and CC is A. So in this way, this is a group, and V is a commutative group but not a cyclic group. Now remember that the previous result says that image of a cyclic group is the same. Homomorphic image of a cyclic group is cyclic. So because Z4 is a cyclic group, so phi of Z4 must have to be a cyclic group. So let me write that down. So here I am just writing over here. So let me write down, since Z4 is cyclic, so from the previous results, phi of Z4 must be cyclic, but here phi of Z4 is whole set V. Because why the whole set V? Because we assume that this is onto homomorphism, but V is not a cyclic group, so which is a contradiction. So why we achieve contradiction? Because why we achieve contradiction? Because we assume that the mapping phi is an onto mapping, which is not. So there is no onto mapping. So we cannot assume that there must exist an onto mapping from the group Z4 to the group V. So there is no such onto homomorphism. So that's how the result is complete. So in this way we can show that there is onto homomorphism or not. So let me quickly give you an exercise. Can you solve this exercise? So let me quickly give you an exercise. So let me write that down. So this is this exercise for you. Show that there is no onto homomorphism. Sorry, let me group homomorphism onto group homomorphism from the group. So what about the group? Let me write down the group Z plus, from the group Z plus to the group Q plus. So Z plus is a cyclic group and Q plus is a let me I just ask you to, is this Q plus is a cyclic group or not? So check that, is there exist onto homomorphism. Q means the collection of all rational numbers, so Q plus is a group, but is this a cyclic group or not? Find that out, and from there talk about that there is a no onto homomorphism from the group Z4 to the group Q plus. So here basically we achieved the all the results we have achieved we can achieve the results from that applications. Also, I just want to inform you, we just completed our syllabus on the group structures. So from my next video I will going to talk about the ring structures, so which is a structure, which is algebraic structure with two so a set with two algebraic structure. Ring is a set with two algebraic structure. So I hope that you will come back in my next video. So till now, stay safe and thank you for watching.